All right, so let's look at a first example here. Pretty simple one. Um, we are to graph y equals 1/2 x squared. Now, the typical way to graph a function, if we don't know any shortcuts or patterns, is just going to be to make a table of values. So all we're going to do here is make a table, an x and a y chart. With any equation, we can choose an x value and then evaluate to find the y value. So for the x value here, we're going to choose like 0. So plug in 0 into that function. Plug it in, right? You get 1/2 times 0 squared. 1/2 times, you plug in 0, and you evaluate that expression, which is the function rule, and you get 0. So that is a point on the graph, and we're going to plot that. That's really all we're going to do in this problem is just pick points and then plot them. So if we kept going here and I said, well, what if we plugged in, let's plug in like a 2, or let's plug in, well, let's start from there. If we plug in 2, we would have 2 squared, which is 4, and then half of that is 2. So 1/2 times 2 squared is going to be 2. So now we have the point 2, 2. So we can plot that. And what if we plugged in, let's go ahead and plug in 4. If I plug in 4, I would get 1/2 times 4 squared, which is 8. So I'd also have the point 4, 8. So we have that right there. Now, because this is symmetrical, you're going to see that if we plug in these negative ones as well, if I plug in -2 or -4, we're going to get the exact same thing. And you can think about why that happens when we do this expression. You know, why if I plug in -2, why does that give me the same thing as plugging in +2? Well, think about that, right? We're squaring something, so we're going to get the exact same thing because it's going to make it positive. And if I plug in -4, again, I get the same thing as +4, which is 8. So I have these points right here, -2, 2, and -4, 8. And so I can plot these right here and this right here. Once we have enough points and we know what the parabola is generally going to look like, we can sketch it. So we just sketch this in here, fill it in, and draw some arrows on it. And you might notice the problem also says, how does it compare to y equals x squared, right? So remember, this is like the parent function. This is the most basic function we can have. Well, if I put the parent function in green on the same graph, let's graph that as well, right? So if I plug in 0 into x, I get the same 0, 0 response. If I were to plug in 1 into this function, I would also get 1, so that would be like right here. If I were to plug in 2 for my x, I would get 4, and so that would be higher than the other one. 2 would go to 4. 1, 2, 3, 4. That'd be up here, right? And if I were to plug in, let's just say 3, well, 3 squared, of course, is 9. So if I plug in 3, I get 9. Now, because everything's symmetrical, I could just bring this over, basically, and I would have these points. So the green portion here, or the green graph, would be the parent function, and then the black graph is what we just graphed right here, the 1/2 x squared, right? We plug in some points, we get some y values, and then we plot those points and sketch a smooth curve. How does it compare to the parent graph? Well, because of this 1/2, because we said 1/2 times x squared, think about what that's doing. It looks like it's just wider. It looks like this is just stretched out, kind of stretched out the parabola and made it wider. Okay, so you're going to start to notice some of these patterns, and we want to kind of go back to how are these translations or how are these things changing in comparison to the parent function. All right, let's try another one. All right, so example 2 says y equals -2x squared plus 4. All right, so the same thing, if I wanted to sketch a graph here, I would just make a table of values and then plug in values for x. And so I'm going to plug in 0. and I'm going to evaluate these. You could go ahead and try this yourself and fill out this table, or you can follow along. If I plug in 0 into the equation, okay, we would be plugging in -2 times 0 squared plus 4, and we would have to evaluate that. Now, you could be using your calculator to figure these out, but when we evaluate this, we should get 4. So that means that 0 goes to 4, right? And then we could plug in more values, right? And it's just sort of an experiment. So if I plug in 1, what do I get? I'm just going to cut right to the chase here. I'm going to get 2. So if I plug in 1, I get 2. That's going to be right here. If I plug in 2, and I take 2 squared, which is 4, times -2, that'd be -8 plus 4, that'd be -4. So if I plug in 2, you're going to see that I get -4. So 2 goes to -4. That's right here. Now also, because I know this is symmetrical, if I plug in -1 or -2, it just so happens that those are going to be identical to the ones I have above. So that's also going to give me 2 and -4. So that means I'm going to have this point right here and this point right here. And so that's how I graph that second example. Notice how we have the symmetry here. We also have the vertex of this parabola. The vertex here is at 0, 4. It moved up 4, right? And that's because we had this plus 4 right there, right? So the graph shifted up. And also in comparison to y equals x squared, what else can we say, right? This parabola is not opening up, it's opening down now. So we don't have a U shape, we kind of have an upside down U shape now. And that's because of the negative coefficient there. If you remember back in chapter 1, we graphed these absolute value functions, right, that were like these. A lot of the stuff we're talking about here in terms of vertex and if something is opening up or down is going to be very, very, very similar to same patterns that we're seeing here. Because we have a -2 out in front here, it's going to be opening down, and that's what we're seeing in this graph right here.